Hello everyone, in this video you'll be learning about the front end of the compiler. When you write a program in C or Java, the program cannot be directly executed by the computer. To execute the source program, which is the original program written in one language, needs to be translated into the machine code. And this translation process is done by the compiler. That is, the compiler translates the source program written in one language into an equivalent target program in another language. The target program is usually a machine code that can be directly executed by the computer. As an alternative, the interpreter can directly execute the source program with inputs from the user to produce the outputs, and the interpreter can give better error diagnostics because it executes the source program statement by statement. However, the advantage of using compiler is that the machine code produced by the compiler can be much faster at mapping inputs to outputs over the interpreter. The compiler can be divided into two parts, which are analysis and the synthesis parts, which are also called as the front end and the back end respectively. The analysis part breaks up the source code to generate the intermediate code representation, and the synthesis part generates the machine code from the intermediate code representation. Optionally, some compilers have intermediate code optimizer between the analysis and the synthesis part. This figure illustrates the components of the compiler, and the analysis part can be further divided into three phases, which are the lexical analyzer, syntactic analyzer, and the intermediate code generator. The lexical analyzer receives the character stream from the source program to generate the token stream, and the syntactic analyzer constructs the syntax tree from the token stream, and the intermediate code generator generates the intermediate code representation from the syntax tree, and the intermediate code optimizer optimizes the intermediate code representation to pass it to the code generator, and the code generator generates the machine code from the intermediate code representation. In the following, I'm going to be discussing about the front end of compilers. The lexical analysis is also called as the scanning. It is done by the lexical analyzer. Suppose we have the source program as position equal to initial plus rate times 60. The lexical analyzer breaks up the source program into the character stream, and the character stream is grouped into a meaningful sequence called lexeme, and for each lexeme, the corresponding token is generated with a form as token name and the attribute value, and the ID is the abstract symbol for identifier, and for this symbol we have assign as the token name, and plus for this plus symbol, and ID identifier for this lexeme rate, and number for this constant 60, and the attribute value is a pointer to the entry in the symbol table, and the symbol table holds the information about the identifier. And the lexical analyzer looks up the symbol table to pass the tokens to the parser to create syntax trees. So how can we specify lexeme patterns? We can use regular expressions, and the operators in arrays to specify patterns are described below. So union and concatenation, collinear closure, positive closure, they have these operators, and here are the examples of above operators. A union B gives the set of A, B, and A union B concatenate A union B gives the set AA, AB, B, A, B, B. B cleaning closure is the strings concatenated 0 or more times. So the symbol epsilon indicates the empty string. So if the string B is concatenated 0 time, we have epsilon and B, BB, BBB, and B positive closure gives us the set B, BB, BB, which is the set of B clinic closure without the empty string. And these arrays can be transformed into finite automata. There are two types, non-deterministic finite automata and deterministic finite automata for finite automata. And let's first look at the non-deterministic finite automata. In the string of A's and B's, including the empty string, can be expressed as A union B clinic closure, can be written as A clinic closure union B clinic closure, gives the strings epsilon A, AA, AB, ABB. And the following illustrates two examples of automata for language of A union B clinic closure and language of A clinic closure union B clinic closure. So the left one, we can, by following the edges state 0 to 1 A epsilon, we have string A because A epsilon is concatenated and gives the string A. And let's look at AA. We can go from start state to state O 2 times and go to 1, and it will give the string AA. So this automata shows us that we can derive strings of A union B clinic closure, and the non-deterministic finite automata is composed of the edges and the states, and the final state is represented with 2 circles. In the right example, it accepts language of strings composed of A concatenated 0 or more times, or B with B 1 or more times. So let me repeat that. It is the language of strings either with A or B with 1 or more times. So you can have A or AA, or B from state 0 to 3, 4, and BB by going to O3, 4, and 4 again. And if we want to have more B's, we can repeat this final state. So the upper right automaton accepts the string AAA by through the states 0 by following the edge epsilon to 1 and following label A 2 and A again 2 and A again 2. So this epsilon is going to be concatenated and we will end up with the string AAA. And now let's look at deterministic finite automata. The earlier examples of automata are non-deterministic finite automata, NFA, and NFA allows several edges with the same label leaving from a state, and it permits moves with epsilon on an empty string. On the other hand, the deterministic finite automata DFA differs from NFA in that it allows several edges living from the same state. Actually, it should not allow several edges living from the same state, so I'm going to correct it. So the deterministic finite automata, it does not allow um, several edges living from the same state, and there are no edges labeled with epsilon. So we have the start state here, NFA accepting A union, and the union can be also read as or, so A or B, clean closure A, B, B. So starting from here, this both NFA and DFA on the right, we have O 1, 2, 3, and DFA accepting A or B, clean closure A, B, B. So both NFA and DFA accept the same set of strings ABB, AA, BB, AAA, ABB. And the difference between them is that on the left it has two edges living from the same state 0, but on the right DFA it does not have more than one edge living from the same state. So looking at the DFA, it generates string ending with ABB with A's or B's with prefix. So let's see whether we can have AB, ABB, for example. So we can go A from 0 to 1, and to reach B, we can go to 2, and to reach A again, go to state 1, and B, B. And this route can be done by the NFA A, B, A, B, B, A, B, A, B, B. So you can try by yourself other examples whether these strings can be derived from both automata. So we can transform the regular expression to non-deterministic finite automata. So if you define a language with regular expression to specify the lexeme patterns, you can transform it to the NFA. So create NFA for each symbol and each operator. So we can use Thomson's construction. So if we have edges A and B, we create non-deterministic finite automata for symbol A and B as state O, state 1 with final state, start state, and final state, NFA for A, and this one shows the NFA for B, and NFA for A clean closure. You can transform this automata to this by having edge label going to the start state and connecting them with epsilon edges with new start state and final state, and connecting the final state from to the start state. And when you concatenate NFA for AB, you connect with epsilon, so we have SO to SO should be S1 and S2 to S3, and A epsilon B, and this one shows the NFA for A union B. So start state, you connect with epsilon with new start state and final state, and you connect the start state of the label A with epsilon and B with epsilon, and the final state connected with the final state of the this with automata with the label A with epsilon, and this state 4 with epsilon, which is the final state, which has been the final state of the automata with the label B to the new final state with epsilon. So if we follow these rules to transform the regular expression A union B connected closure ABB to the corresponding NFA, first we try A union B. A union B will have this form, so you can see this form here, A union B, and with connected closure you follow this rule, so you connect H epsilon H to here, and epsilon H again with new start state from A union B, new start state and new final state, you connect with epsilon, and with the following ABB, because they are concatenate, you just concatenate with epsilon, but you can simplify by removing epsilon because they keep the same string. So by connecting them with the corresponding labels, we have A, B, B with final state 10 with start state 0, which gives us the NFA for the corresponding NFA for the given regular expression A union B connected closure ABB. So you can transform the NFA to DFA, and this one I'm going to resume from the next video. So I'll stop here for today. Thank you for listening, and see you again in the next video. Bye bye.